mathematicians. Today we see a very nice linear algebra problem asked in CSIR June 2018. Let A be a m by n matrix and B be a n by m matrix over real numbers with m less than n. Then we have to discuss about invertibility of AB and BA. So AB is always non-singular, AB is always singular, BA is always non-singular, BA is always singular. Okay. So if we can visualize matrices as a linear transformation, then this problem is immediate. So it is a part B problem, so you cannot spend like more than 2-3 minutes. So let's see how to approach this problem. So if you are new to my YouTube channel, please subscribe to my channel. If you like my videos, please click the like button and share with your friends also. So let's continue. So main thing to notice is that the main assumption given is m less than n, that we have to keep in mind. So AB, what is AB? Like if when you apply AB, the product of two matrices on a vector V, what will we do? It is A of B of V. First you let this matrix B act on the vector V, so you get B of V. After that, this B of V is now a vector, so that vector you on that vector A will act. Okay, so that is how we calculate AB of V. So even though we are writing AB, actually first we are writing B only. That is the observation. So let's see. So now AB, so we are going to apply first B. B is a n by m matrix. Okay, so if it is a n by m matrix, then it is a linear transformation from r power m to r power n. Okay, so from r power m to r power n, always remember it going the other way. Then A is a m by n matrix. So then it is a linear transformation from Rn to r power m. So together AB is a linear transformation from r power m to r power m, but it is going through r power n. Okay. Similarly, BA is a linear transformation from r power n to r power n. In between, it goes to r power m and then it come back to Rn. Okay. Now, suppose AB is invertible. Okay, that means that this AB is as a linear transformation from r power m to r power m. It should be a bijective linear transformation. Okay. Similarly, if BA is non-singular, then it should map this r power n to r power n bijectively linearly. As a linear transformation, it should be bijection also. Now, here we use the condition that m less than n. Okay. So, if you noticed, so now this r power n has a dimension bigger than r power m because of this condition. So, when you apply A to this r power n, what happens is, so since this has a dimension less, now the image of this r power n here will get decrease. Okay, it cannot be n here. Okay, it will be reduced. Maybe it can the image of r power n under this linear transformation A can be at most m, and m is strictly less than n. Now what we do, this B we are apply only on the image of A. When you compose, you note that, so when you calculate A B of V, B of V only we are applying in A. So the vector belongs to range of B is what applying to A. Therefore, similarly here also the vector belongs to range of A only get applied on B. So range of A will be subset of this r power m. So range of A will be some vector space of dimension strictly less than n. And if on the range, if you apply this B, it can never be Rn because range is some space strictly less than n. So from a vector space V whose dimension less than n and to r power n you have a linear transformation B, then definitely this image cannot be r power n. Now what is range of B? Now B is a linear transformation from r power m to r power n, and this r power m has dimension lesser than r power n because of our condition m less than n. Okay, so now therefore the range of B can be dimension at most m. Let's see why it is so, because now for this matrix B we apply the rank nullity theorem. Okay, so what is the domain of so B is a linear transformation from R power m to R power n. So by rank nullity theorem, the dimension of the domain m is equal to nullity of B. What is nullity? Dimension of the kernel of B plus dimension of the range of B, that is equal to rank of B. Okay. Now even if this number is even if this number is 0, this rank can be at most m because of this equality. Okay, note that this is a non-negative number, this is a non-negative number, non-negative integers, therefore this number can be maximum m, right? So this is the rank of B. Therefore this range of B can have dimension at most m, and m is strictly less than n. Therefore, range of BA can be of dimension at most m. It cannot be n. Therefore, BA is singular. Okay, BA is always singular from this observation. So, in the third option, they are saying that BA is always non-singular. That is false. Okay, if this statement is correct, then this statement is false. Now, let's come to talk about AB. In the first option, they are saying that AB is always non-singular, but we can take B to be zero matrix. Then the product will be zero matrix. Which will be singular. Okay, so we can simply eliminate this option is wrong. What about whether AB is always singular? So in this example, we are getting AB is singular. So the question is, okay, whether are we getting AB always singular? That is the question. No, the answer is not true. Not that in case of BA, we are going from bigger dimension to smaller dimension, then to bigger dimension. Okay, so that is some sense not possible, because when you are going to smaller dimension, you are losing some dimension. Okay, because of you are losing some dimension here, you cannot go back to R power n again. But now here this is smaller dimension. From smaller dimension to you are going to bigger dimension. Here the dimension, you can make sure that the dimension remains same. If B is invertible, then here the dimension of the range of m will be m. From here to here, again you can go to, so this is a range of B here can be dimension m. From dimension m to dimension m, you can always get a biject. You can find a bijective map A. Okay. So for suitable choice of B and A, this AB can be invertible. From R power m to R power m, you can go, because in the middle you have a bigger space. So from 2 dimension to, you can go to some 3 dimension. So inside this 3 dimension, you take some 2 dimension. So from this 2 dimension to you go to 2 dimension. From here you can again go to 2 dimension. That is possible. But here this is 3 dimension, this is 2 dimension. From 3 dimension to 2 dimension you cannot go. So if you go, the dimension will be reduced. So again you cannot go back to dimension 3. I'll give you one example also. We take A to be 2 by 3 matrix, B to be 3 by 2 matrix. We will see that this following AB is non-singular. What is the matrix? From B is R2 to R3, XY goes to XY0. Okay, note that inside this R3 we fix a R2 and I send this R2 to R2. Here we are not losing any dimension. Again, here you take any vector here, XYZ, and you send it to first two coordinate XY. Okay, so XY0 in particular will goes to XY. So if you look at the composition of these two map, XY is finally going to XY. Therefore, AB is a identity. So AB is invertible. So if you learn something new in this video, please click the like button and share with your friends and subscribe to my channel. Thank you.